Lesson 2. Operational Mathematics for Business Efficiency. Welcome back, intrepid learners. Today, we're zeroing in on the operational side of business mathematics. Operations are the engine room of any business, and mathematics is the fuel that powers efficiency and optimization. Get ready to see how theory translates into operational excellence. Linear programming for resource allocation. In the quest for efficiency, linear programming stands as a beacon, guiding businesses in optimizing resource allocation amidst constraints. Linear programming is a mathematical approach used to optimize resource allocation in a business setting. It involves setting up a mathematical model and using algorithms to find the best possible solution that will maximize profits or minimize costs while taking into account various constraints and limitations. This method has wide-ranging applications in fields such as manufacturing, supply chain management, operations research, and transportation, among others. The goal of linear programming is to find the most optimal solution by maximizing or minimizing an objective function, which is a mathematical representation of the goal of the business. This objective function is subject to constraints, which are limitations on the amounts of resources available. Constraints can include factors such as budgetary restrictions, time limitations, and the availability of materials. One of the key strengths of linear programming is its ability to handle complex problems with many variables and constraints. It allows businesses to make data-driven decisions, taking into account various factors that may affect their operations. By using linear programming, businesses can optimize their resource utilization and maximize their profits, leading to improved efficiency and competitiveness. Another important aspect of linear programming is its ability to provide multiple solutions depending on the specific objectives and constraints considered. This allows businesses to explore different scenarios and evaluate the potential outcomes before making a decision. By considering various options, businesses can make more informed and smarter decisions, leading to better overall performance. Moreover, linear programming can be used in combination with other mathematical or statistical techniques to provide a more comprehensive analysis of business problems. For example, it can be combined with sensitivity analysis to determine the impact of changes in parameters on the optimal solution. This not only helps businesses make better decisions but also allows for ongoing monitoring and fine-tuning of operations. Case study: manufacturing optimization. Consider a furniture manufacturer juggling production lines for chairs and tables, constrained by labor hours and material costs. One possible production process for a company would involve building chairs and tables separately, with dedicated production lines for each item. This process would involve setting up separate production lines for chairs and tables, each with a specialized team and equipment, and managing the flow of materials and labor between the two lines. Alternatively, the company could use a parallel production process. This would involve setting up a single production line that is capable of producing both chairs and tables. This production line would be staffed with a flexible team that is trained to work on both types of products. Materials and labor would be shared between the production of chairs and tables, allowing for improved efficiency and cost savings. Another option for the furniture manufacturer would be a mixed production process. This process would involve setting up one production line that is capable of producing both chairs and tables, but the production would be done in a sequential manner. This means that the production of one type of product would be completed before moving on to the production of the next product. This process would allow for a more specialized approach to production, as the team working on each product would only have to focus on one type of furniture at a time. The final option for the furniture manufacturer would be a just-in-time (JIT) production process. This process would involve producing furniture only when it is needed, minimizing inventory and waste. The production line would be set up to quickly switch between chairs and tables, based on demand. This process would require careful planning and coordination to ensure that materials and labor are available when needed, but it can lead to significant cost savings and increased efficiency. Ultimately, the best production process for a furniture manufacturer will depend on their specific goals, resources, and market demands. Each process has its own advantages and trade-offs, and it's important for the manufacturer to carefully consider their options before making a decision. Regardless of the chosen process, effective management and coordination are key to successfully juggling production lines and maximizing productivity. Through linear programming, we'll explore how they maximize profit while navigating these constraints. Linear programming is a mathematical optimization technique utilized by businesses and organizations to make efficient decisions while considering various constraints. These constraints can include limited resources, time, budget, and legal regulations. By using linear programming, businesses can determine the best course of action that will result in the maximum profit or desired outcome while adhering to these constraints. In the context of the fashion industry, companies may face multiple constraints when producing and selling their products. These can include a limited budget for purchasing materials, a strict production timeline, and regulations regarding fair labor practices. Additionally, there may be limitations on the availability of certain materials or the demand for particular styles. To effectively manage these constraints and maximize profit, fashion companies can use linear programming. This involves formulating mathematical models to represent the company's objectives, constraints, and decision variables. The objective may be to maximize profit, minimize costs, or achieve a certain level of customer satisfaction. Decision variables in the fashion industry may include the number of pieces of each style to produce, the amount of fabric to order, and the pricing strategy for each product. These variables are interrelated, and the goal of linear programming is to determine the optimal values for each variable that will result in the most profitable outcome. For instance, a fashion company may use linear programming to decide how many units of a particular dress to produce given the available budget for materials, the production timeline, and the expected demand for the dress. By considering these constraints and utilizing linear programming, the company can determine the quantity of dresses to produce that will result in the highest profit margin. In addition to maximizing profit, linear programming can also be used to optimize other key performance indicators, such as minimizing production time or reducing waste. This can help fashion companies become more efficient and competitive in the market. Exercise. Solve a linear programming problem. Using a simple linear programming model, calculate the optimal production mix of chairs and tables to maximize profits, given specific constraints on labor and materials. To calculate the optimal production mix of chairs and tables, we will use the following linear programming model. Objective function. Maximize profit equals 8x plus 5y, where x equals number of chairs produced, y equals number of tables produced. Constraints. 1x plus 2y is less than or equal to 200, constraint for labor hours. 3x plus 2y is less than or equal to 300, constraint for materials. X is greater than or equal to 0, non-negativity constraint. Y is greater than or equal to 0, non-negativity constraint. Solving the model using a linear programming calculator, we get the optimal production mix. Number of chairs, x, equals 100. Number of tables, y, equals 50. This means that to maximize profits, the company should produce 100 chairs and 50 tables. This will result in a profit of $800, 8 chairs x $8 profit per chair, plus $250, 5 tables x $5 profit per table, equals $1,050. It is important to note that this is just an example and the actual optimal production mix may vary depending on the specific constraints and profit margins of the company. Inventory management models. Next, we step into the world of inventory management, where mathematics ensures businesses have the right stock at the right time without tying up unnecessary capital. One of the key principles of inventory management is the optimization of inventory levels. This involves using various mathematical models and algorithms to determine the optimal level of inventory for a business to keep on hand. This is based on factors such as demand forecasting, lead times, and production constraints. Optimizing inventory levels helps businesses avoid stockouts, when a product is out of stock, and excess inventory, when a product is overstocked, both of which can be costly for a business. By using mathematical models, businesses can accurately calculate the optimal levels of inventory to maintain, taking into account various factors that can affect inventory levels. One commonly used mathematical model in inventory management is the economic order quantity (EOQ) model. This model calculates the optimal quantity of a product to order by balancing the carrying costs of holding inventory against the ordering costs. Another important aspect of inventory management is the safety stock level. This refers to the additional inventory kept on hand to protect against unexpected changes in demand or supply. The calculation of safety stock levels also involves mathematical formulas, taking into account factors such as lead time variability and demand forecasting accuracy. Mathematics also plays a crucial role in inventory management through inventory optimization software. These software systems use advanced algorithms and data analytics to analyze various factors, such as sales data, customer demand, and supplier lead times, to determine the most efficient and cost-effective inventory levels for a business. In addition to optimizing inventory levels, mathematics is also used in inventory management for other tasks such as inventory forecasting, replenishment planning, and inventory cost analysis. These tasks involve using mathematical models and calculations to make data-driven decisions and improve the overall efficiency of inventory management. In summary, inventory management relies heavily on mathematics to ensure businesses have the right stock at the right time. By using mathematical models, algorithms, and software, businesses can accurately calculate optimal inventory levels, reduce costs, and improve their overall supply chain management. Case study: Retail Inventory Optimization. A retail chain uses the economic order quantity (EOQ) model to minimize holding costs and reorder frequencies. The EOQ model calculates the optimal quantity of inventory to order based on factors such as demand, lead time, and holding costs. To begin, the retail chain needs to determine the demand for their product. This can be done by analyzing historical sales data and considering external factors such as market trends and seasonality. Next, the lead time must be determined. This is the time it takes for the retailer to receive new orders after placing them. Lead time can vary depending on suppliers and shipping methods. The retailer must also consider the carrying or holding costs associated with holding inventory. This includes costs such as storage, insurance, and the opportunity cost of tying up money in inventory. Using these factors, the retailer can then use the EOQ formula to calculate the optimal quantity of inventory to order. This formula takes into account the annual demand, holding costs, and lead time. Once the optimal quantity is determined, the retailer can then set a reorder point. This is the inventory level at which a new order should be placed in order to avoid stockouts or excess inventory. The reorder point can be calculated by subtracting the lead time demand from the optimal quantity. By using the EOQ model, the retail chain can minimize holding costs by ordering the right amount of inventory at the right time. This can help improve cash flow and reduce the risk of overstocking or stockouts. However, it is important for the retailer to regularly reassess their demand, lead time, and holding costs in order to maintain an accurate and effective EOQ. They may also need to adjust their reorder point based on any changes in these factors. Additionally, retailers may also use other techniques, such as just-in-time inventory management, to further optimize their inventory levels and reduce costs. However, the EOQ model remains a valuable tool for retailers to use in their inventory management strategies. Analyzing their strategy reveals the delicate balance between stocking too much and too little. As a manager, it is essential to find the right balance between stocking too much and too little inventory. Keeping too much inventory can lead to increased storage costs, risks of spoilage or product obsolescence, and tying up much-needed financial resources. On the other hand, having too little inventory can result in lost sales, dissatisfied customers, and missed opportunities. One way companies maintain this balance is through demand forecasting. By analyzing past sales data and trends, companies can estimate future demand and adjust their inventory levels accordingly. Companies also use just-in-time (JIT) inventory management, where they only order and receive new stock when it is needed, helping to reduce excess inventory and related costs. Another strategy to achieve this balance is through supplier relationships. Companies work closely with their suppliers to ensure a constant supply of goods, without the need for excessive inventory levels. In some cases, companies may even utilize vendor-managed inventory, where suppliers manage inventory levels on behalf of the company. In addition to these strategies, Companies may also employ safety stock levels, which are extra units of inventory kept on hand to cover unexpected spikes in demand. This helps to reduce the risk of stockouts and keep customers satisfied. Moreover, companies are leveraging technology to optimize their inventory management. Supply chain management software and data analytics allow companies to track inventory levels, monitor demand, and make more informed decisions about when to order new stock. By carefully balancing these strategies, companies can optimize their inventory levels, reduce costs, and satisfy customer demand. As a manager, it is crucial to regularly review and adjust inventory management strategies to find the right balance and ensure the company's success. Workshop. Calculating EOQ. Total cost equals 10,000 x $0.005 plus 10,000 divided by 2 x $0.0002. Total cost equals $50 plus $1. Total cost equals $51. By ordering 10,000 units at a time, the total cost of ordering and holding inventory is minimized. This exercise highlights the practical benefits of mathematical models in inventory management. Inventory management is crucial for businesses to ensure the smooth operation of their supply chain, avoid stockouts, and minimize costs. However, managing inventory can be complex and challenging, especially for companies with a wide range of products and fluctuating demand. This is where mathematical models come in handy. Mathematical models use quantitative techniques to represent real-world systems and optimize decision-making. In the context of inventory management, these models can help businesses determine the optimal level of inventory to meet customer demand while minimizing costs. Let's explore a practical example to understand the benefits of mathematical models in inventory management. Suppose a retail store sells electronic gadgets and has an annual demand of 20,000 units for a particular product. The supplier offers a bulk discount for orders over 5,000 units, which decreases the cost per unit. However, the store also incurs storage costs for holding excess inventory, which increases as the inventory level increases. The cost per unit and storage costs are as follows. Cost per unit for orders up to 5,000 units, $10. Cost per unit for orders above 5,000 units, $8. Storage cost per unit per year, $2. Now, the store has to decide how many units to order to optimize its inventory and minimize costs. This is where a mathematical model, called the economic order quantity (EOQ) model, can be applied. The EOQ model uses a simple formula to calculate the optimal order quantity that minimizes the total cost of inventory. The formula is EOQ equals square root 2ds h, where EOQ equals economic order quantity, D equals annual demand, S equals cost per unit, H equals holding cost per unit. In our example, using the EOQ formula, the optimal order quantity for the retail store is 6,324 units. This means that the store should place an order for 6,324 units to minimize its total inventory costs. To further illustrate the benefits of using mathematical models in inventory management, let's compare the results of using the EOQ model with the store's current ordering strategy. Suppose the store currently places orders of 10,000 units at a time. Using the EOQ model, the store's annual inventory costs would be $21,583, including the cost of ordering and storing. However, with the current ordering strategy, the annual inventory costs would be $24,000. This means that by using the EOQ model, the store can save $2,417 in inventory costs per year. Moreover, the EOQ model can also help the store maintain optimal inventory levels. In our example, the store's current ordering strategy may lead to excess inventory, which incurs high holding costs. On the other hand, using the EOQ model, the store can order smaller quantities more frequently, reducing the risk of stockouts and minimizing inventory holding costs. In conclusion, mathematical models, such as the EOQ model, provide practical benefits in inventory management by optimizing order quantities and minimizing inventory costs. They enable businesses to make informed decisions about inventory levels and ensure the smooth operation of their supply chain, ultimately contributing to their overall success and profitability.